Okay. Um, and so our agenda um, was here. Oh, um, I guess I have to minimize this window in order to scroll through it, huh? So, yeah, to finish the permutation descents problem, which we tried to do by brute force and ran into the problem of having to search through all 99 factorial permutations of 99 elements, which turns out to be a bit more than we can chew. And so we looked at the pattern of numbers. Well, let's just go there. All right, so that's here. Right. And uh, just remind you the problem given an integer n, a permutation of order n is a one-to-one mapping right onto itself. So that's a permutation of 1, 2, 3, 4, 5, 6, 7 onto itself, where 1 goes to 5, right? And so forth. Um, so then permutation descent count function, um, if you have 3 elements and there's no descents, then there's only one way of doing that: 1, 2, 3. There's 3 elements and there's 1 descent. Well, there's 4 ways of doing that, and there they are. You can just, guess and check them basically. Or are we following some sort of pattern here? Um, you can't start with 1, 2. So you could start with 1, 3, and that's the only way to start with 1. You could start with 2 in 2 different ways, and you could start with 3 in only one way. So yeah, what's the logic of that? Yeah, so here was the sample input and producing this output. So we've already talked about this one. 2, that's just a line number, right? So if you have 5 elements and you want all the permutations, to count all the permutations with 2 descents, turns out there's 66 of them. So that would be kind of hard to list out. I listed out the first couple of them here, but yeah, 66 probably not worth. Well, you might find a pattern in there. I should probably have started with um, 1, 2, 3. There's only one way to start with 1, 2, 3, which is to finish with 5, 4. Oh wait, no, we want 2 descents. So if you start with 1, 2, then you could go 5, 4, 3. Is there another one that starts with 1, 2? No, unless there is, and I'm not thinking of it. No, I think you have to have 2 descents, and the only way is to go 5, 4, 3, right? So you say, okay, well, is there one that starts with 1, 3? Well, sure. 1, 3, 2, 5, 4, that would do it. And like I say, you could explore that. That'd be a good sort of thing to do while you're waiting for a bus. Do people wait for buses anymore? Um, you're in the doctor's office. Yeah, that's. Oops. Yeah, that killed my light. Um, there. Okay. Excuse me. Seems to be somewhat of an imbalance there. Okay, if I do that. Okay. Uh, so, right. Okay, so this was the problem, right? This 9950, the fourth element there, the fourth entry. We weren't getting a response on that, right? So we got the response on 8.3. There are 15,619 um, ways of doing that. So what we discovered was that we were doing some experiments here, right? We were seeing these numbers. Um, 1. Well, I don't know. Where were they? Yeah, 1, 4, 11, 26. Right. So we looked up the sequence in the OEIS, um, and the OEIS comes back and says, yeah, well, those are the Eulerian triangular numbers. Oh, so we look up the Eulerian triangular numbers, and let's see. Can I? Yeah. So if I ask for my PDF viewer, it doesn't necessarily give me just any PDF viewer, huh? Just it's stuck on the textbook one. And well, let me show you how I find this article, um, which is to go to a browser. And where's my browser here? Um, and this is something else which we don't need, so I'm going to go to maa.org. This is the Mathematical Association of America, and they've got all kinds of things going on, but generally speaking, they require a membership. And so I am fortunate enough, well, I pay good money. Does that make me fortunate? I suppose so. And let's see, that should work, right? Okay, it's a little bit slow, but yeah, so it remembers me, and then I go to my subscriptions, and I'm going to say search. Okay, I think I just say member access to these journals. Okay, and I got like decades of these journals, which would require me centuries to read. But I read the occasional article, and I have access to this database, right? So I want to search for, oh, I don't know, Eulerian triangle. The problem is that there's okay, this is the one. Um, there's Euler's triangle, which is that's a geometric construct, and this is the two-sided Eulerian triangles. Okay, so I'm going to go here and say, yeah, I want this PDF, and here's the article. Now, it's very mathematical. This is from Kyle Peterson at DePaul University. And he starts out with a quote from Giancarlo Rota, who writes in Indiscreet Thoughts, I will shamelessly tell you what my bottom line is. It is placing balls into boxes. Not sure what the context. Oh, he was a professor at MIT from 1959 to 1999. Arguably the father of the field known today as algebraic combinatorics. He had 50 students, notably Richard Stanley. Yeah, I can't say as I know that name. It rings a faint bell. And as of this writing, he had 329 mathematical descendants, including many of the top names in the field today, and including Kyle Peterson. If putting balls into boxes is good enough for him, well, it should be good enough for any of us. So in this article, we will first give a gentle introduction to the permutation statistics and Eulerian numbers, followed by an explanation of how to use the idea of balls in boxes in this setting. We then will take those ideas and study. Well, yeah. It would take us a while to read this article, and as you can see, it is sort of intensely mathematical. But yeah, so the descent of W, we can skim it a little bit here. Descent of W is the count. So you see there's kind of an absolute value around this whole thing. So that's the count of the set of all r's such that the inverse of um, W composed with sigma sub r is less than the inversions of r. Uh, yeah, or inverse, right? Um, yeah, so that would require a little bit of sussing out. But see, here they are, the Eulerian numbers, um, in a sort of triangular form, right? Your internet connection is unstable. It's telling me over here. Really? Um, network internet access. I seem to have a wired connection. Yeah, video intermittently blurry because of that, unfortunately. Hmm. Well, let's hope that clears up. What else are we going to do? Uh, Give me a holler if it's terrible, or we'll do something. Okay, so yeah, so n is the column number here, and I is, sorry, the row number, 1, 2, 3 up to 8, and I is the column number 1 through 8. So yeah, so we have, I'm going to scroll on further here. So there's a generating function. So this is good stuff. This is worth reading. So the generating function for Eulerian numbers with n fixed is denoted this way. And you can see that's sort of similar to what's going on with this generating function. What's a generating function? Well, never mind. What does this have to do with putting balls in boxes? Yeah, well, it's sort of a partitioning. So you see 5, 6. So you have a partitioning of the numbers 1 through 6 here um, into groups of increasing sets, right? So 5, 6 is an increasing set, perhaps, but then decreasing between those, right? So 5, 6, 2, and then 2, 1, and then 4, 3. Right? So those are those descents. And so here's a formula for the coefficient, where this is a combinatorial expression, the number of ways of choosing n things from n plus k minus 1. So this is the number of ways of choosing your descents, but then you're going to be adding those up and getting these Eulerian numbers. And so essentially, this is kind of where I want to cut chase to here, right? This right here kind of tells us what we want. We want a recursive formula, which you see here at the top, right? That's a n comma I is given in terms of a n minus 1 comma I and a n minus 1 I minus 1 with those coefficients, right? So if you're on the first row in the first column, that's this top knob here. That would be A1, 1, and that's just defined to be 1, right? We don't plug that into that's what's called a base case. So you don't actually plug that into this formula, right? And in fact, the base cases are going to be along the left side and along the right side, where if I is 1, then the output is 1. You don't bother plugging into the formula. And if I equals n, then you're 1, right? So it's only, this is the first one right here in the middle where you would plug into the formula, right? And what would we have? This would be third row, second column. I'm saying third row because we're along here, right? and second column because we're on this, thinking these columns are sort of left going diagonals, right? So this is third row, second column. That gives us a fourth, right? So A32 is 2 times A22, which is 1. So this is a 2, right? Plus N is 3, right? And I is 2. So this is also 2, right? Times A21, which is 1. So this is 2 times 1 plus 2 times 1, that's 4. And you can see it more clearly in the diagram here, right? So these are the multipliers for the, so you get the 4 by 2 times 1 plus 2 times 1, and you get this 11 here by 2 times, well, sorry, this 2 times that 4 and plus 3 times that 1. So you can just sort of follow the pattern in here, right? So let's go to our code, and I can say, look, yeah, that's what I've got here with my Eulerian function. So I just sort of copy and pasted, more or less, that recursive formula here for reference. And then I have the base case, right? So this is a recursive function. You see that Eulerian here is calling Eulerian and Eulerian again, and that's kind of where this gets to be a problem, because for every single call to Eulerian, you have potentially 2 more calls to Eulerian, and some of these are going to be the same call, that is, with the same parameters. Okay, and now you may also notice that I have something else here, which is a 2-dimensional vector of ints. So this is like a matrix is a 2-dimensional vector. It has, rows and columns, right? And why do we need that? Well, maybe it's worth going off on a sidebar. Let's talk about, yeah, probably too many people are using Zoom. No doubt. All right. So, as a sidebar, so here's my browser. I'm going to go searching. I don't think I need this page anymore, so I'm going to search for, how about a simple Fibonacci so memoization is a new word for today, maybe, or not. But oh, I remember her. Yeah, this is a Python lady. So we don't want to go. Maybe we should put C++ in our search here, right? Because we don't want to. Memoization. This is Geeks for Geeks. They've got a little thing on memoization. We've got code review and Stack Exchange. Okay, I go for that. Recursive memoized Fibonacci in C++. So yeah, let's go back to the code window, and I'm going to get out a blank sheet here. So I think I can exclude this, yeah, and save it, and then get a new one here. So I'm going to add new item, and it's going to be Fibonacci. Have we talked about Fibonacci? I talk about Fibonacci a lot, so I'm never sure if it's a new new topic for a group or not. Fibonacci, Leonardo da Pisa, lived in 13th century Italy, I believe, although he was a merchant and traveled from Pisa all around the Mediterranean. and beyond to India, um, where he learned about Hindu Arabic numbers and their Hindu Arabic number system, and brought our place, what we now think of as our place value system, to the Western world, that is to Italy, and uh, that spelled the end of Roman numerals. Before that, yeah, it was still Roman numerals. So I don't know. Should we get a little, since we're doing a little history lesson here while we're at it? Um, so in my browser, I've got this going here. I just want to make sure I know where that is, and we can go to this. Here's Alex Stepanoff. We don't care about him anymore. So how about Fibonacci history math? There he is. And I tend to avoid Wikipedia. I don't know why I don't like them. Um, but yeah, 13th century. That was correct. Um, we've got the story of mathematics. We've got St. Andrews. Yeah, this was my putative destination where I was to deliver a paper this summer on um, spherical trigonometry. That is not happening. Damn it. Although I still have the plane tickets. Anyway. So yeah, he's the son of, yeah, whatever. But yeah, I don't want to go too far out on this tangent. But yeah, so here are his numbers. And he gets these numbers by saying a certain, let's see, where, certain man put a pair of rabbits in a place surrounded on all sides by a wall. How many pairs of rabbits can be produced from that pair in a year? If it is supposed that every month each pair begets a new pair, which from the second month on becomes productive? That's a question. So you have one pair of rabbits, but they're not productive yet. So after 2 months, you still just have one pair of rabbits. But now that's a productive pair, so they produce another pair of rabbits. So you have one productive pair and one unproductive pair, which means you'll have 3 pairs of rabbits, 2 of which are productive, right? So each month, you have the previous month's rabbits. No rabbit ever dies. And then 2 months previous, you will get those again because they're productive, right? So you're always adding the number 2 before to the number 1 before to get this number, right? So 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21, and so on. So we'd like a way of producing these, right? So we go back to our code and say, yeah, I can, okay, so who am I? What am I doing? Oh, I don't know. I am working on Fibonacci. All right, and what am I going to do with Fibonacci? I'm going to include the usual suspects. And let's put in vector here, just because vector, right? And so now I'm going to have a function called Fibonacci, and it's going to take 2 integers. Well, I guess only 1 integer, right? Yeah. So we want to know what is the nth Fibonacci number. And we'll have a base case, right? And this is the way recursion generally works, right? You want to have a base case, so we're going to say if n is 0 or n is 1, then we're going to return 1. Those are the first 2 Fibonacci numbers are 1 and 1. Otherwise, we're going to return. It's key to use this return value here, right? We're going to return a call to Fibonacci of n minus 1 plus Fibonacci of n minus 2, right? So if we get a Fibonacci of 2, then that won't be one of the base cases. We'll then return Fibonacci of 1, which is a base case, that's 1, plus Fibonacci of 0, which is another base case, that's also 1, and so we'll return 2, right? All right, that's fairly simple, and it's a nice example of a recursive function, right? So in main, we'll query the user for some integer n, and we'll say while, so we prompt, maybe we should use a do while. Is that a good occasion for, so cout enter n to find the nth Fibonacci number, okay, and so then we're going to say yeah, I think I have to do the prompt here, right? All right, yeah, you'd think I would know how to do simple things like this without fumbling. Okay, so I'm just going to do it like this, right? So while cin n, and then cout what? How about Fibonacci of n equals Fibonacci of n. Notice I haven't put any fail-safes in here, right? If you wanted to make this more bulletproof, go ahead. Then I'm going to prompt again, right? And there's probably a cleaner way of doing all that, but this certainly works, right? So that'll put it in an infinite loop, and let's see how this works. Okay, so how about 0? Yep. That's, I should put in a return, right? Yeah, here. Okay, so 0. Fibonacci of 0 is 1. 1, that's also 1. 2, that's 2. 3, 4, 5, 6, 7, 8, 9, 10. 11. And there are all sorts of patterns at work here. Notice that Fibonacci of 11 is a square number. Fibonacci of 10 is a prime number. And I should say that these things are not hardwired. You know, sometimes this is called Fibonacci of, sorry, I should be showing you the output. There, is that better? Yeah. So I was saying that sometimes the first Fibonacci number you count at 1, right? So F1 is 1, F2 is 1, F3 is 2, and so forth. So I'm kind of off by 1 here, depending on how you count. If you count the other way, then you'll notice this pattern that this would be a 5, that's 5. This would be a 10, that's 55. And 14 would be a 15, that's 610. So the pattern there is that every fifth Fibonacci number is divisible by 5. This is among the many interesting facts about Fibonacci numbers. So 15, how about 99? Okay, so we're sitting and we're waiting and we're wondering, why does this take that can't be taking that long, can it? I mean, it didn't take very long to get the 15th Fibonacci number. And yet here I am still filling dead air with commentary about how long it takes to compute the 100th. Is that the 100th Fibonacci number or the 99th? But yeah, we're still waiting. So perhaps it would behoove us to look at. So I'm back in the code window. We're still waiting, right? So over in the code window, I'm looking at this debug. The call stack is kind of what I'm interested in here. And it's not going to actually show me the call stack. I'm looking over in here, and I'm not seeing anything either. I think if I want to see this call stack, I have to put a breakpoint in there. So let's go back to the output. See, do we have it yet? Nope, still waiting. Okay, so I'm gonna stop this and put a breakpoint in here. Here, maybe? Is that a good place? And then run this again. And let's not go too far over the edge. Let's just say, okay, I want the 20th Fibonacci number. And it's going to pause here. So while we're pausing, let's go back to the code window and see what do we have in the call stack over here. What is the call stack? Oh, can you? Okay, I guess I'm not sure if I put the photo. Okay, so yeah. What is the call stack? It is a stack in memory. Stack meaning like first in, last in, first out, LIFO. Last in, first out, LIFO. That's LIFO, and that's a kind of a data structure where, you think of it as a stack. The one you have available is the one on the top, right? And so every function call leads to a call, traces the function call on the call stack. And so if I hit F10, what happens here? Oh, well, it goes back to the oh, so it's waiting for another. Okay, so that didn't make my point very well, did it? Let's see. So if I enter in, oh, I don't know. So 20 should have given us plenty. Let's look at 14. So that doesn't take long to execute, but maybe putting the breakpoint in the wrong place. I don't know. So this is the call to Fibonacci, right? So if I hit F10 here, and then hit the code window. Whoop. Code? Okay. This is hard to read, isn't it? But you see that Fibonacci returns 610. So I think that's the problem. I need to put my breakpoint over here in the call to Fibonacci. Maybe here, huh? Okay. So let's try it that way. So I'm going to compile and run this here, and I'm going to enter in 20. And over here we see in the call stack, if I hit F10, yeah, so that's a little more like what I wanted to see here. So back to the code window. You see that we're on line 10, and we're calling Fibonacci. We now have two calls on the function stack, right? So line 17 was the call to Fibonacci, and then we have two calls to line 10, which is, compute Fibonacci and Fibonacci again, right? So now if I hit F10 here, I see, whoops, I get another call to Fibonacci. Okay, and then I'm going to hit F10 again. I've got another call. I'm going to hit F10 a few times here. And then over here in the code window, you can see I've been building up this huge stack of calls to Fibonacci, and you can see that what I entered in 20 and n is currently 13, which means, you know, I've called Fibonacci of 19 and Fibonacci of 18. Then for 19 we call Fibonacci of 18, and Fibonacci of 17. For 18 we call Fibonacci of 17 again, and Fibonacci of 16. And then each of those doubles, right? So you're going to have how many function calls here? I don't know. Let me keep hitting F10 for a while. So now n is down to 10, n is down to 9, 8, 7, 6, 5, 4. I'll get back to the code window here in a minute. All right. So, but yeah, you see all these stacked up calls to Fibonacci? That is clogging up the works, and that is causing the delay. All right. So you get too many. You can get a stack overflow. That's the origin of that phrase, and that's exactly what's happening with 99, right? So how do you address this issue of stack overflow? 99 is a gigantic number. Perhaps we need to change to long int. Oh yeah. Somebody commented on that. Yes. Sure. Let's go ahead and do that. And so we'll make a couple of changes to our code. I'm going to stop that and say, yeah, we're going to return not an int, but I think int 64 underscore t is a 64-bit int. That's the same as a long, right? So we can take, you know, the input is not going to be a long number, but the output potentially will be. I think that's okay. That oh, let me think about that. Yeah, the inputs are never going to be nice. So you're never going to have a. So if the original input is 99, you know, all these will be smaller than that, right? And okay, so yeah, it seems to be happy with that. So let's take away this breakpoint. But then, so what we would like is this concept of memoization, which says I don't need to compute all these numbers over and over again. I just need to compute them if I haven't already. If I've computed them already, I can just look them up. Where? Well, in some sort of container, perhaps a vector of ints. So I'm going to have here a vector of ints called memo, and I'm going to set it equal to, I don't know, 100. Is that enough? And all of them will be -1. So this is the way of initializing a vector to have 100 elements, all of them -1, right? Okay. And the -1 is just a flag. It's saying if I haven't set this already, then it'll be -1, right? So then in my Fibonacci function, I'll say if memo of n minus 1 sorry, if memo of n, I think, oh, and of course this is a vector, right? So if the nth element of memo is not equal to -1, then return that. Right? I've already computed it. I'm just going to look it up and not compute it again. So I won't. Then that won't be a recursive call, right? That'll just be a lookup. Lookups are relatively cheap, right? You're just finding a place in memory and returning what's there, right? No call stack need be involved. Uh, Function call stack. And so, um, right. Otherwise, um, what am I going to do? I think I do want an else here, huh? I'm going to so I want to record the value that I'm getting, right? So I want to say memo of n equals um, I guess Fibonacci of n minus 1. Okay, I'm not thinking about this the right way. Let me skip over to the browser so I don't take too much of your time with this. Um, let's see, where are we? Is it here? No, this was that history thing. Not that either. Oh, this was, yeah, here. Okay, so okay, I guess if I zoom in too far, okay. Right, so yeah, right, that's what I'm forgetting, that we want to actually pass the vector along with the call to Fibonacci, right? So uh, so this is initializing, which is what we did on just one line, right? So let's okay. So here's the prototype for this function. Oh, and he's using a pointer to an int as a way of getting an array called memoize. And I'm not using an array. I'm using a vector, which is fine. Um, and but yeah, so we need to pass in. So let's go ahead and do that, and then maybe I can get it from there. Um, so my Fibonacci function should take a vector of ints, a vector of int 64 objects, right? Which I'm going to call memo here, and then probably change this as well, right? Because those are the Fibonacci numbers, and they can be quite large, right? And so we're passing that vector along with it, and so here now I have oh. Do I want this to be a global variable? I don't really, do I? I can take this in here. It's probably a better place for it, right? And then we'll pass it along with our call to Fibonacci. So should we go? Well, let's see. So I need to call Fibonacci of memo. And pass that along with the thing. And I guess we need it here as well. Oh, well, yeah. Let's skip on back to the browser for a second. So how's he dealing with this? Okay, so here's the definition of Fibonacci. And it says, if it's equal to -1, then we need to calculate it, right? Okay, so that I just am doing it backwards, or maybe my way would work. Um, can we recover my way? So here he's got computing memoization if, yeah, and then return memoize of num. Okay. Uh-huh. Okay. Yeah, so that may work. Um, I'll just keep with the way I'm doing it because it's perfectly fine. So I guess I want this here, right? And then we'll just return memo of n. Oh, I could just put return here, right? Can you do that on a single line? I don't know. Is this going to work? Yeah, so here I need to call Fibonacci with memo. Okay, I don't see any IntelliSense tingling. Is this worth a go? Let's give it a go. So if I go to the output window, and I'm going to compute 0. Yeah, that's good. 1, that's good. 2, looking good. 3, 4, 5, 6, 7, 8, 9, 10. All of these are fine. So how about skipping by 10? So 20. I went pretty fast. 30. Nah, it's a little bit slower. Quite a bit slower. Okay, but it produced it. Well, let's go with sorry, a little delay there. Thinking about entering 40, is it okay? So why was it so slow with 30? Or maybe it wasn't that slow, right? I mean, we didn't try the other one with 30, so we don't know that it was slow. 40 seems to be kind of a long time. We could do a bench test with the chrono and compare the two different Fibonacci's. Yeah, 40, which is actually the 41st Fibonacci number, depending on how you count. So maybe I should have entered the 39th here. But yeah, that's still pretty slow. It's going to be a fairly large number, I guess. So, yeah, that's pretty slow, huh? Should we go back to our code and see why is it so slow? So we're saying if it's not equal to -1, then just return the thing. Okay. And so, but if it is equal to -1, that means we need to compute it, which for 0, we just return 1. Oh, I'm wondering, yeah, we should probably load up the first couple of, do they do that in their example? Should we go back to the output window, see what's done? No, it's still waiting. Yeah. So that does seem a little slow. Let's go ahead and kill this and see if we can't speed that up. And let's go back to that browser. Do they initialize the memoize with something here? They have I will assume that n is bigger than 2 just to keep it short and simple. So yeah, they do set the first two, and they say the first Fibonacci number is 0. That's another way of sort of starting off on the right foot, huh? Okay, so um, let's do that. Okay, so I'm going to go back to my code window and say um, a memo of 0 is 0 and memo of 1 is 1. Okay, then in here, um, do I want these base cases here now? So I guess I would return n in those base cases, right? So if it's 0, then return 0. If it's 1, then return 1. Um, then we're going to say if it's not equal to negative 1. I don't know. I suppose that will... I should think this through before doing the execution. But let's see if it's a little faster, right? So here's the output window. And I'm going to say, yeah, give me the 20th Fibonacci. That was pretty fast. Give me the 29th. Yeah, it's a little slow again, right? Okay, but it's got it. The 30th. Yeah, it should be about the same time as the 29th, maybe a little bit longer. But notice that that's divisible by 5 now, right? Because 30 is divisible by 5. And so if I say 35 here, I get out my forthcoming book is Things to Do While You're Waiting for Your Computer. I was watching ACM video. That's the Association of Computing Machinery. In the function else is not necessary. Yeah, good point. Because you wouldn't get there if you weren't going to get there. So there's 35. Anyway, I was feeling some dead air here. This ACM video about the history of computer graphics and talking about the state of computer graphics some 40 years ago and how long it would take to produce a frame. You know, just produce a single frame in a video would take hours. So, you know, if you consider how many frames, if you have, 60 frames per second, I don't think they have that many, but if you were to have 60 frames per second and each frame cost hours, then you're talking, weeks or months to produce a short little clip. And so that's why the first applications of computer graphics were to advertisements for cars, typically. Okay, we're still waiting. Oh no, there it is. Sorry, I wasn't paying attention. Okay, so but still that's pretty slow, and we'd like to make it faster if possible. And with the getting rid of the else, if return that. Otherwise, yeah, and right, we don't need the else. Which then, for the call to Fibonacci, say you have Fibonacci of 2, right? Then memo I don't think we need this if then, do we? Because Fibonacci of 2 is equal to negative 1, right? So we would return the result of assigning to memo of 2 Fibonacci of 1, which, okay, I'm not doing this right, am I? Let's go back to the browser. So yeah, what if we turn that around? You suppose just turning it around, so it's going to say if memo is equal to negative 1, then I'm going to calculate it. And in either case, when I'm done, I'm going to return memoize. Okay, so let's try it that way. See if that doesn't speed things up a bit. Which, yeah, I should be more logically deductible about. Deductible, that's April 15th kind of word. Deducible? Um, okay, so I'm going to say here if so just get rid of this, right? If memo of n equals -1, then compute. I think I could just do this, right? Yeah. So if that's true, then do this computation, and in any case, return memo of n. Eh? Okay, and there's a comment here. Unless n is negative. Okay, right. But yeah, I think we won't have that problem because memo of 0 is not -1, right? We set that equal to 0, and so we return 0. Right. So let's give this a shot. So let's just check the base case, make sure it works. Yeah, we changed this to be 0 and 1. 2 is also 1, right? 0 plus 1 is 1. 3 is 2. 5 is 5. 10 is 55. 15 is 610. 25, that was pretty, 20, a little bit slower. 30. It came back with something. Was that a little faster than before? I suppose we should benchmark these things to find out, right? And then we need to return to our permutation descent problem and see what's going on with that. It's very similar to this, right? In the sense that each recursive call doubles the number of function calls. Okay. And 35. Yeah, it's taking about the same length of time as it took before, huh? Which is an unconscionably long time. But I think when compared to the one without memoization, it's a lot faster. All right. Maybe we don't need to wait for this. We've already seen what the result of it is. And it doesn't seem to be a lot faster with my new arrangement. Alrighty, there it is. Right, and all right. So let's bring back our caddis problem, which was this descending permutation descent problem, and so here we have this. I'm doing the same thing, right? I've got a vector of ints called memo, or vector of ints called memo. Right, and so here the thing is that these, yeah, the Fibonacci number has only one index, right? So you get the nth Fibonacci number, whereas these Eulerian numbers have two indexes, k and n, or sorry, n and I guess is what we're thinking of is here, right? And so that's why I need to have a two-dimensional array for my memoization vector. I want to know what row and column it's in. You could probably get by with a one-dimensional array. Just multiply by the triangular numbers to get to the next row. Right. So the third row starts with the fourth element because the second triangular number is 3, and then the row beyond that starts with seventh element because the third triangular number is 6, right? And so you could get by with a one-dimensional array, but that would require more thinking, and this will work just fine. So I guess the trade-off is maybe extra memory. Are we using more memory with a two-dimensional array? Yeah, I guess. Memory's cheap. Okay, so our Eulerian, now we have 2 indices instead of just 1, right? N and I, and the recursive formula is here, and the base cases are and I am kind of doing this the backwards way, right? Should I try the same approach as where is it? Fibonacci here. In Fibonacci, I'm just saying if the memo is -1, that means I need to compute it, and then I just return it. I kind of like that approach. Should we take that approach? Oh, where am I? I'm in a completely different world. Oh, I guess I didn't open this up properly. Okay. Okay, so I'm sort of scrapping my base case here, which makes me a little uncomfortable, but I'm going to say if this is -1, then I'm going to compute it. And I think this code was not correct the way I left it off, so don't be confused by the fact that. So I'm going to compute. Oh, I think I want to do this, right? So if this thing is -1, then I want to compute this thing according to that formula up there, right? Which is I times memo of n-1, just reading it off there. Oh, yeah, two-dimensional array, you have to index like so, right? We haven't done two-dimensional arrays, really, have we? I don't know, any questions about that? Get used to it. So I guess the way to think about this is that this memo of n-1 is a vector of integers, right? So which integer in that vector of integers do you want? Right, so memo is a vector of integers, right? So which vector of integers do we want to start out with? Well, this one. I tend to think of that as the row, right? When do we get to set to -1? I think that's down here. Yeah. Oh, and that's bears discussion as well. So I've got I think the Caddis problem said that these numbers, the number of this permutation size would not be more than 1,000. So I set that as my maximum, and so I want 1,000 by 1,000 array of -1s, right? And so how do you initialize that? Well, you're going to say memo of m is going to be a vector of 1,000 vectors, right? M is 1,000, right? So we've got a vector of 1,000 vectors, and each one of those vectors is going to have 1,000 entries, each -1, right? So, and I had forgotten how to initialize a two-dimensional array. So you just look it up on Stack Overflow, right? That's what that's for. So you know how to initialize two-dimensional vector in C++. You know, ask the great sage in Stack Overflow or whatever your flavor of internet search is, and it will spit back something like this, right? So recall that I think you could do this in 2 steps as well, right? You could create a vector of ints called v, and say I've got 1,000 of those, each one -1, right? And then I think you could then put that here, right, as v, right? So, but why do it in 2 steps when you could just do it in 1? All right, so good question. How do you do that, right? So this is how you initialize a two-dimensional vector to be 1,000 by 1,000, 1,000,000 -1s in a square array. Okay, and maybe should we initialize the first couple of them just to be sure? And so what does that mean? Well, that's going to mean memo of I don't know, is it 0, 0 we want to start out with? Oh, that's a bit of a concern, isn't it? So that's going to be 1. You can cascade these things, right? You could say that's memo of 1. See, now we have this off by 1 problem, right? So if the second integer is a 0, then it's going to be a 1. And if the 2 integers are the same, then it's going to be a 1. And that kind of thing can drive you wild. Okay, but the way this is read from right to left, right? So the 1 is assigned to memo of 1, 1. That's a 1 now. That's assigned to memo of 1, 0. So that's also a 1. And that's assigned to memo of 0, 0. So all 3 of those entries are 1s. I suppose we could add a few more. But I think that'll get us. I'm not even sure we need that, right? In any case, back up here to our Eulerian function. And we have it currently returning a size t element. All right. We may want to make that an int 64, because these could get to be large numbers. I'm not sure. In any case, so we're saying if it's a -1, then we need to compute it, which means, okay, so we're kind of off by 1, right? This is confusing. So should we make this I plus 1? Because we're off by 1, right? But I think then this, since n and I are both off by 1, if we had n plus 1 minus, in parentheses, I plus 1, then those 1s would cancel out. So this is still just going to be n plus 1 minus I. So the difference between n and I plus 1 times memo of n minus 1 and I minus 1. Whew. Maybe we need to test this, huh? In any case, then we're going to return, and I'm not going to delete that, although not going to be needed like that anywhere. So now we're just going to return memo of n I, huh? So we just computed that. If we needed to compute it, we computed it. Otherwise, we just look it up, right? Yeah? Alrighty. Well, I had this working to where I could, so I have a little for loop here to test that this works, right, before I even get into the caddis input, right? In fact, let me move this down to here because that's part of the caddis business, right? So I just want to see, do I get, okay, so now this is actually going to start at 0 instead of 1, huh? Make this strictly less than, and strictly less than. Well, let's give that a whirl. Does it even compile? No. Oh, I have two different mains going on because I have my old Fibonacci here. So I need to remove this, exclude it from the project. Okay. And I've got a range error. Subscript out of range, which you can't see that, huh? Oh, if I go to the output window, you don't see this little range error window, which it says debug assertion failed. You've got a range error somewhere. Okay. Oh, it's printed out of 1, huh? Okay, I'm not sure what. Okay. Oh, and that's where my range error is, somewhere in there. So we initialize this thing to have 1,000 by 1,000 negative ones, right? So we're only going up to 8 here, right? So I'm not sure. I've got code that seems to work for the first 3 cases, but seems to head into an infinite loop with the last case. Okay, but so why am I getting a range error? And where does that occur? It's the nature of range errors. They tend to not to tell you. Okay, so I've got this initialize thing here, but this is not being ever called as far as I... Yeah, I don't call initialize anymore. So should I just comment that out because it's sort of distracting? Same thing with this descent thing, right? So let's just get rid of all that because that was part of the old way of doing things by brute force, right? So now this is going to take n and I and compare if it's negative 1. So there shouldn't be a problem here, right? I mean, these are, unless my initialization here is not... Shall I, how about I just comment all of this out and see out, well, how about a little for int I equals 0, I less than 8, increment I. I'm just going to test to see what I've got here. I don't see why there's a range error. J less than 8. Increment J. I'm going to see out what is it, memo of I, J. These should all be negative 1s, right? followed by a tab, let's say, and then followed by a new line, and that shouldn't have a problem, should it? Oh, N is an undeclared identifier. Okay, well, let's just take this comment thing here, put it here. Oh. Okay. Okay, so there's my 8 by, oh, yeah, here. There's my 8 by 8 array of negative ones. Okay, so that's working fine. And what we would like is I guess, oh, I just want to get rid of this for loop now, right? And do it like that. So should we just pause here? See if that's a problem. That doesn't seem to be a problem. Okay, I'm looking at the output window here. Okay, which is blank, right? And then I press enter and I get my range error. Okay. So I'm calling Eulerian with my memo. And N and I are just going from 0 to 7. We know that those are all filled up with negative ones. So why, I mean, this, like, we're not reaching outside, are we, somewhere? Oh, I see. So if I is 0, then this is a negative 1 here, right? Oh, crap. So is it this off by 1 thing that's causing me the problem? Let's see. Jonathan has some code here. So PDC of NV. Yeah, you're not doing memoization though. Sorry. I'm going to insist on some memoizing here. So, the problem is here, right? Yeah. Yeah. I'll tell you what, I can, if people want this code, I could just upload it to the discussion page. I mean, as it is, so you can edit along with me here. I don't know if that's productive or what, but I'll give it a whirl. So here we have the browser page, and if I go back to here, yeah, there's our agenda. Oh boy. Okay, so I'm going to attach here something somewhere. Okay, doesn't like it for some reason. Oh, is that okay? So that's a posting a reply. Okay. Oh, I didn't actually post the agenda yet. Okay, and there it is. If you want to grab it there. Um, as it stands, it doesn't work because of those n-1 and i-1 elements there. So let's go back and look at those again. Um, so what are we trying to do? Consider the case where we're calling. Oh well, what's the first call here? It's going to be to n is 0 and I is 0, and so we're calling Eulerian with our memo together with 0, 0, right? And that's obviously going to be a problem because when we go up here, yeah, that's a -1. But we have to, I think this is where we kind of need to have our base case, right? Okay. So if you've got a -1 and so yeah, I think we need to put in our base case here, right? So in fact, we could copy this, paste it in here, right? If I equals n or I equals 0, I think is what we want to say here now. Then we're going to set memoization memo of n I equals 1, right? That's the base case where you're at the edge. And then we'll do this as an else. I think we will need an else here, right? So if I is not 0, what if n is 0 and I, yeah, see, I is always less than n, right? So you can't have n equals 0. Well, maybe that'll work now, right? So I just needed, oh, why is it underscore? Oh, I don't have, okay, a curly brace. So if we have a base case, then we're just going to do that. Otherwise, we're going to do this. And in any case, we're going to return that. All right, let's give that a whirl. It kind of starts out promising with the 4. That 4 looks good there. What are these numbers? Okay, back to the drawing board here. Oh, you weren't seeing that, were you? Let me show you what I'm getting there. Output. Yeah, see, I'm getting this 1 and 1, 4. This should be that, you know, Eulerian triangle, right? So this should be 1, 4, 1, actually. And then this should be 1, 11, 11, and then followed by a 1. Okay, so we're going down here looking at this little, this is just to test that it's working, right? And it's not, so why not? So we're going from I equals 0, I less than n. If n is 0, so maybe n needs to start at 1 here, huh? Oh, sorry. That's the problem. I need to look at both places simultaneously. Thanks for the reminder. Um, so I'm thinking, yeah, if we have n starting at 1, then you would have I equals 0, which is less than 1, and we would call 1, 0. Oh, okay. Let's put this back to 0, right? Because we have that off by 1 thing going on, and we'll just put a less than or equal to here, and let's see if that what happens. More spaghetti on the wall. Okay, well, here's the output. Um, you see, we are getting these first few rows now correct, right? Um, and we're getting the one on the outside each time. That's good. Nice. That's the because that's a base case, right? But then we're getting these garbage values in between, and why is that? Um, okay, so in the case where, well, what's the first? So we were getting 1 1 4 1, right? So that's A00, A10. All right, I'm confused again. Oh yeah, A1 1, right? So those are all ones, right? So if we go back to the paper, so we can look at that. So this is in the browser, or we have is it this thing here? Yeah. Um, so so I'm thinking of this at the top as being A00 now. This is A10. This is A11, right? Are we getting those correctly? Again, running this. Looking, yeah. So we're getting those, right? And we're also getting A20, A21, and A22, right? Those are coming out 141. That's what we want, right? And then we're getting A30 is 1, and the first problem is with this A32. That's not coming out correctly. So let's go look at that. And I want to do that here. So what if we call down here n is 3, oh, and I is 1, right? A31 is the first one that's not working. So if we call A31, or Eulerian of, n is 3, I is 1, right? And we're just passing the memo along for the ride. Maybe that should be the third parameter, but never mind. Then it is going to be a -1, right? Because we haven't set it, right? So A31, or sorry, memo of 31 will be -1. So if I equals n, well, that's not true. If I equals 0, well, that's not true. So we're not going to do this. So we're going to do this, which is to set memo of 31. I'm writing this down with pencil and paper. Memo of 31 equals, so I is 1, so that's going to be 2 times memo of 2, 1, which is 4. Oh. Okay. Yeah, right, because we want to get 11 out of this, right? So then that's going to be plus 3 plus 1 is 4, minus 1 is 3 again. Yeah, so it's going to be plus 3 times memo of 2, 0, right? Which is 1. Yeah. And so that's going to be 2 times 4 plus 3 times 1. So this should give us, I don't know. Should we put a breakpoint there and check to see what's going wrong? Okay. The problem with this breakpoint is the F10 is also the hotkey for switching to the output window, and I haven't changed. I meant to change that, so that means we keep going back and forth between the code window and the output window, and you don't want to necessarily. I forget how you change the hotkeys. So let's see how are we doing. Oh, James is here. That's good. I didn't see you come in. This must be that back door. All right. Let's see. So, right. So we want to know why does this not come out as 11, right? Because we should be setting this array value to 11. That's what my pencil and paper computation comes out to. And then returning that value, right? Okay, so F5, compile and run. Go to the output window. What's it waiting for? Oh, I don't know. I guess it's here. Okay, so we go to the code window. What do you see? Nothing, huh? If I press F10 to go back to the code window, still see nothing. Where are we? There should be a yellow arrow somewhere saying where we are, right? I'm scrolling about, I know, but because I don't see any yellow arrow. Okay, F10 again. I'm just going to keep pressing F10 until we get to, well, where are we now? F10, F10, F10. Doesn't seem to be anything going on here. This debugging thing is not working. Okay, well, we can do the old-fashioned debugging, right? Which is to when in doubt, see out, right? So I'm going to print out see out here. I guess, what do I want to see? I want to see I plus 1 equals I plus 1. Should we say times? I don't know. Memo. Oh, I want to actually say times memo of n minus 1. I equals memo of n minus 1 I it should be plus, right? put in this n minus 1 minus I. Let's insert that directly into the output stream. Times memo of n minus 1 I minus 1. I know this is tedious. Equals memo of n minus 1 I minus 1 and end line and pause. All right. I don't know. We're using memo of n minus 1, but we don't know if it's a negative 1. That's a comment there. Is that true? Oh, so this should be like the Eulerian call here? Oh, that could be a good thought. Well, let me, since I went through all the trouble of, yeah, that's incisive. Thank you for that. Oh, do I still have that breakpoint going? Okay, so, oh, I do still have this breakpoint going. So it's back at the breakpoint. If I say F10, then it skips on to there. F10 again, 10 again. I'm just keep hitting F10 here. Right, so, but memo of 20 is negative 1. Okay, and so why it gives me, but yeah, so let me take the suggestion that we've got on the table here that rather than calling these memo values here, so let me comment out this debugging stuff here. And this should be a call to Eulerian, huh? Well, the whole point of memoization is that we don't want to have multiple calls to Eulerian. And so we want to consider the base case again here. So so here's this base case, right? So if we're at sort of the right side so that I equals n, or we're on the left side so that I equals 0, then we want to set memo equal to 1 and return that. So in the case where we're calling memo of 3.1, that's where we run into problems. And we get memo of 2.1, which has been set, and memo of 2.0, which has also been set. So neither of those should be negative 1, and yet they are. It's right here. We're setting memo of 2.1, for instance, right here. Memo of 2.1 gets set to 4, right? So the next time we're looking it up, we should get a 4 here, right? So if n is 3 and I is 1, then this is memo of 2.1, which we set to 4 on the previous call, right? 20 was set to 1 back over here as well, right? Okay, well, let me take this breakpoint out because I want to see what happens with this. Some serious debugging here, folks, and then we need to take a break here in a few. Okay, so I guess we're waiting for a CN here, right? So we get 1, 1, 1, then 1, 4, 1. So that's correct, right? But then what happens here? We get garbage. I plus 1 equals 2 times memo of 2, 1, which is negative 1. But didn't we set memo of 2, 1 equal to 4? Oh, I think I know what's going on here. When we pass memo to Eulerian, we're passing it by value, which makes a local copy of memo and writes to that. What do we want to do instead? Don't everybody answer at once. Thank you. For not all answering at once. Yes. So if we pass by reference here, that should fix this problem. So let's just take this out again and see that it does fix the problem. And yeah, you can be long in the tooth and still make beginner errors. But yeah, that's starting to look good now, right? Yeah, that's what we wanted to see. If we go to our see this 247, 420, 4293. Well, yeah, it's not showing here, is it? Do we have a more robust list? Who knows what's going on with it? I haven't read this whole paper myself. So there were some other papers here which might be of some interest. Let's see, was it here or here? Oh, yeah, see, this wasn't working. There's more memoization stuff. Here. Right. So, should I, let me post this link up here in the, so you can see. I'm not sure how I got here, but it's some reference to Eulerian numbers that's not password protected. So if we go to our discussing page, I can paste that in if you're interested in looking at that as well. Okay. All right, I think we're ready to finish this up. Good God. Well, and the hope is that this actually makes it fast enough to pass muster. All right, so here we are in our code window, and we've tested out that it works. Now we want to answer the caddis question, right? And so I'm just going to comment out all of that. And what are we going to do here? Yeah. Oh, I'm not sure. I may be off by 1 here. Oh. Yeah. I don't know. Oh. Well, we'll just see, right? Okay, so I'm going to take our, we'll just guess and check. I mean, I suppose that shows me to be the lazy bum that I can't hide the truth about. Okay, so here we got this. Do Alt Shift. Okay, and Control C. So that's the input I want, right? So if I say F5 now, I get to my output window. I paste in the results and I get nonsense. Okay, why? So I'm getting my number of input lines. I'm getting the item number. I'm getting K. Shall I call those N and I just to be sort of consistent with so if I use this as a lowercase n and use this as a lowercase I, then, you know, I'm kind of thinking along the same lines maybe. So N and I, maybe not such descriptive. Well, yeah. So here's N and I, and I think we may want like N minus 1 and I minus 1. Would that help things along? Let's try that. I think this 1, 1 is correct now, right? But the 5 is clearly not, and neither are these. They're all the same garbage number. Why? Actually, this should be a 4, shouldn't it? Going back to the expected, yeah, 1, 4, right? So, yeah, if we enter in 3, 1, so N is 3, and I is 1, and we're going to call it with 2, 0. 3, 1. That's that should be a 4, right? Did I not? Apparently, okay, so 4, and then 1, 3, 1. Yeah, garbage. Okay. I don't know. Looks like we made some good progress here, but we didn't get it yet. And we got some other fish to fry, so, and we're about up on the break time. Maybe we'll spend some more time on this, but I think we have to move on. And I don't know. Oh, let's see. Yeah. Okay. So I'll put up the agenda here. There it is. Okay. And another caddis? I think maybe not. Let's start up with the Bitwise after the break, and let's take a short break. Any questions before the break? Like, why is my coffee cold? That's my question. All right. Yeah, seeing nothing, I will pause the video and pause the OBS as well. And okay, I think that means we're going there. Yeah. So it occurred to me that just one more thing about this memoization. That with the Fibonacci, I was doing the same thing, wasn't I? Not passing by reference. Um, and so, where is that? Okay, so if I go to my code window, and yeah, we'll fix this, but let's save it for another time. But meantime, let's exclude it from the project and bring in the Fibonacci existing item. Is it just called Fibonacci or something? Yeah. And open that up. And we see, yeah, sure enough. See, I wasn't passing by reference here, so it was recomputing that whole vector each time, right? So, I don't know, why is it suddenly underscored? Yeah, so that was just an indication that it had changed. But let's see if that doesn't improve the performance of this thing. So if I go 20, that was pretty fast. 30. Oh, yeah. 40. Yeah. Oh my goodness. I knew there was something odd about that, right? Um, so, yeah, look how much faster that was then, right? 50 just comes right back. 60, it's almost like there's no, yeah. All right, so that 70, we're getting up there. 80, no problem. That's the 80th Fibonacci number. Memorize it. You never know when you're going to need that on the tip of your tongue. 90? Well, we haven't reached our limit yet. The 100th Fibonacci number. Oh, debug assertion failed. Expression vector subscript out of range. I wonder why. Huh. Did I think maybe I didn't allow for that, huh? Yeah. So abort and close and yeah, right. So here, um, so I can just double that. And now if I say F5 and I go for the 100th Fibonacci number, no problem. 110. It's like a bidding war. Oh, now we go negative, right? And that means that even the 64-bit number is not sufficiently large to contain the 110th Fibonacci number. Okay, just wanted to settle that issue of the memoization actually working to make things faster. All right. And so we'll go back to our agenda. Another caddis, I think another time, right? Yeah. This one caddis has satisfied my caddis satisfaction. Um, for a while. In fact, I'm not satisfied yet, but it's because I haven't finished that problem. But you can see we got everything we need, right? I suppose I could repost that code if you want to fix it. So let's see, where would I do that? Can I edit here and say, yeah, I want to? Oh, you can't post a second thing in the same comment, huh? Okay, so I can say done with that edit and go down here and say, yeah, I'd like to attach yet another something. It's not giving me the attachment dialog. Do I need to say the improved permutation descent or something like this? It still doesn't work. And then if I say attach, I don't get anything. I guess that's my canvas for you. I suppose I could, yeah, we'll get back to it. All right. And if I post reply there, and I say edit that, okay, so now I'm getting the browse. And where was it? Caddis something or other? Caddis Permutation Descent. Okay, I'm going to open that and post that reply. And oh, now you don't have my comment about how it's the improved. All right. In any case, back to our text, huh? And we are not on chapter 17. We are on chapter 6. And exercises. And write a grammar for Bitwise. This is kind of where we left off, huh? And let's then start that again. Let's build it from scratch. Why not? I think I can do this. See no objections. Okay. So I'm going to say exclude this from the project, and I don't know, I'm still in this same project. I know this is setting a bad example. You should probably have a whole new project if you're starting, but then I get too many projects and I don't know where anything is anymore. Of course, if I put things in new projects with the name that would suggest what it is, then it might be easier for me to find things later. I know. That's what secretaries are for. Okay. So I want to add a new item, and I'm going to call this Bitwise calculator. And here's a statement. Oh, let me get the code up here. And here's a statement of the problem. It says write a grammar for a bitwise logical. Bitwise logical expression is much like an arithmetic expression, except the operators are these: the or, the exclusive or, and the and. The complement is the same as the negation, essentially, or yeah, sorry, the these guys are the same. The negation operator and the complement. Those are prefix unary operators that give you all the zeros go to ones and all the ones go to zeros. I think that's right. See no objection from the peanut gallery. I will assume that if somebody knew better, they'd say so. Okay, so how do we get started? Well, I think we should get started with a comment about the what our grammar is going to be, right? So the grammar is going to be that an expression could be I'm going to call it an and term, right? Because the thing is, we have now 3 levels of precedence instead of 2. And by 2 levels of precedence, I mean multiplication and division operate left to right, and those bind tighter than addition subtraction, which operates left to right. But now we have an AND term binds tighter than an exclusive OR term. What do we call that? How about XOR term, which binds tighter than an IOR term, the inclusive OR. So it could be any one of those, or it could be a primary. And what's a primary? A primary could be a number, I guess a bit set number, right? Or it could be an expression in parentheses. And a number is going to be, well, what? An integer literal in bit form. Okay. So we're going to need some prototypes. So I'm going to say that an IOR expression is it's the lowest level or the highest level, right? I mean, essentially every expression is an inclusive OR of other expressions which bind tighter than inclusive OR. And the next highest binding is the XOR expression. Right, so they'll have a function to get one of those and return an int. Or we could have an AND expression. Or we could have a primary, which is, as we said in our grammar. Right, so that sort of matches up with our grammar, right? Now the primary could call an IOR expression, right? So that's the most general kind of expression. And so none of these things are defined, and so they're sort of underlined in green, just to remind us that they need to be defined. Again, we want the token class, and it'll have a public section, which is what kind of token is it? And then I guess rather than double values, now we'll have integer values. And we'll need a constructor that takes a single character and whoops, we'll have an initialization list, which is to say the kind is going to take that character, and the value then is just going to take 0, right? Because this will be an operator token, which won't have a value. And then we don't need anything in the body of our constructor. So just have empty curly braces there. Oh, is that off the map? It is a little bit, isn't it? Sorry. Can I fix that here? No. I guess I just need to make my window a little bit shorter so it doesn't, yeah. Okay. Good. So now we need the other constructor for a value token, and that will also take a character, but then it will take an integer, which is the value. And for that one, we'll have the same kind of thing. But the different parameter list, right? So that, what's that called? Oh, I don't need the semicolon there. That's called function overloading, right? Two functions with the same name but a different parameter list. And how does it know which function to call if they both have the same name? It looks at the parameter list based on what's in the parameter passed to the parameter list, passed to the function, it will do one or t'other. Okay, so then I think that's it for our token class. We don't have any private section here, right? I mean, what would be private? I suppose you could make the kind and the value private, but yeah, I mean, that would protect against somebody trying to directly set those values. But let's pretend we're going to be good soldiers and not do that sort of thing. We wouldn't want Sergeant Bilko to burst a gasket. Okay, so now how about our next class? What's the other class? We need a token stream, right? I think we'll use the principle that we're going to capitalize our class names. You don't have to, but it is a common practice. And again, that's when I type in public, right? And if I hit the colon, the IDE says, "Oh, you mean that this is the public section of a class definition," and so standard procedure is to make the indentation flush with the class. Whatever, huh? So now our token stream is, well, it's going to have a constructor as well, right? So the token stream is the name. Is it going to take a parameter? The token stream contains a buffer and a Boolean that says, is the buffer full or not, right? Is there anything else in the token stream? I don't think so. All right, so, well, let's define this constructor later. We're going to want a get function that will get a token, right, and return that token. We're going to want a putback function. This is different than cin's putback function, right? This is our own definition in our class. And what is putback going to put where? Well, it's going to take a token and put it in the buffer, right? If there's nothing in the buffer, right? So can we could define, let's define them later just to be good Indians. Is that bad? I don't know. Then we're going to have a private section, and that's going to contain our member variables, and so we have a Boolean which is either true or false. If there's something in the buffer, then we're going to have a variable of type token called buffer, which is where we're going to put temporary storage. And we never need to have more than one token in the buffer. Now, and that's kind of the beauty of this program in a way, the way Strustrup has done it, is that you can get by with just keeping track of one unprocessed token. You never need more. Okay, which is not obvious from the get-go, but turns out to be more or less true. Okay, so shall we define these things here? So the token stream, and so in order to define token stream, we need to be in the scope of token, but token stream is the constructor, so it doesn't return anything, right? So we just say, look, I'm in the scope of a token stream scope. I'm in the scope of the token stream class, and I'm going to define the token stream constructor. And what am I going to do with the constructor? Well, I'm going to say the full is false. By default, we'll make it false. And what, buffer could be like 0 or something, right? Oh, we can do this in an initialization. I mean, I could say buffer, and this is kind of odd, right? This is uh, Strustrup does this, and he doesn't really explain how is it that something which is actually a token can be assigned the value 0. It's like it's a null value or something. Yeah, um, that's the way it is. And so now let's do this not with assigning these things in the body, but making use of the common practice of an initialization list, right? So we're gonna and we're gonna take full to take the value false, and buffer to take the value strangely 0. Okay, and so now that's our constructor, right? And does that deserve a comment? What should we say? By default, the buffer is empty at the get-go. All right. How about the what else do we have to define? We've got putback and get, right? Get's going to be a little bit longer, so let's do putback first. And putback doesn't return anything, so it's a void function, but again, it's in the scope of the token stream class, right? And so here's putback. I think it's got the same name as the cin putback. There's no underscore, is there, in the cin putback? I can't remember offhand. But we're going to take a token. Let's call it T. And I don't know why it's underlined like that. Is there a problem? No. Okay, it just wasn't settled with itself yet, the IntelliSense. And so I am going to say if full so if I'm trying to put something back into the buffer and the buffer's already got something there, then I've got a problem, right? And what should I say? Buffer is already full, something like that, right? If I'm going to end with a period, I should start with a capital letter, right? We don't abandon all English grammar, especially when we're doing a parser like this, right? Which is, and why do we have CR underlined? I haven't included any libraries at all. So let's bring them in now. What do I need? IOStream, apparently. Using namespace standard. And as we need other things, we'll bring them in. But I saw here that I was getting a problem with CR, so so then we want to set buffer equal to T, don't we? If we don't throw an error here, then we want to assign. Can we assign a value to a token object? Yes. This so admittedly, a token is our own construct, right? It's our own class definition. It's a variable, abstract variable type, which we created, right? It's not a built-in thing, and yet the assignment operator works. And there are a few operators that will work in sort of the obvious default way for user-defined types. And one of them is the assignment operator. which, what does it do? Well, it just says, I've got this object T with its private data members kind and value, and I'm going to take those kind and value variables and assign them to this um, object of type token called buffer. Sort of, obviously that's what you would do. Things can get more complicated with more complicated user-defined types, in which case you need to overload the assignment operator to have it do more complicated things. But in this case, fairly simple. All right, so now what? I guess we want to pay attention to the clock. I'm not gonna go to 12:30, folks. Once bitten, twice wise. Yeah. So is there something else we want to do here? And we're in doing this, we're sort of reviewing the whole how does this calculator thing work, right? And yeah. I think we want to say now full equals true, right? Because presumably full was false because we didn't throw an error, right? Which actually, this is not going to actually throw an error. It's just going to give us an error message. Okay, so that's put back. What else do I want? Well, let's go ahead and define our get now, right? This is going to be a little bit more complicated. Okay, so and what is get going to return? It's going to return a token, right? And we're in the scope of the token stream class definition, and we're defining get. Okay, and we're going to say if there's something in the buffer, then just return that. Do two things, right? Empty the buffer. So say full equals false, and then return buffer. So that doesn't actually literally empty the buffer, but it's this Boolean value that says, do we care about what's in the buffer or not? And if buffer is true, then yes, we do. If buffer is false, well, there may be something there, but we don't care. We just overwrite it. So by setting full equal to false, we don't actually erase what's in the buffer, but we basically are indicating we don't care about that anymore. So now what are we going to do? We're going to get a character, right? And maybe more than one character, but we're just going to get one character to start out with, right? So C in our character. And then we're going to switch on what that is, right? If that character is a operator character, sorry, we're going to say switch. What kind of operators do we have? Well, we've got or. So we don't have the same operator. We don't have plus minus anymore. We have or. And we'll just cascade these together, right? So case or, exclusive or, case ampersand for and do we have complement and negation? Do we care about those? Case, well, let's just do the complement. We won't do the negation as a separate operator. So that's the complement operator. In which case we're going to construct an operator token, right? So, and then return that, right? Get returns a token, right? And so at this stage where we've gotten an operator token, we want to return um, token constructed from that character. And since it's a single character, that will construct a token whose value is 0, because we don't care about the value. Yeah? All right, so it could be a number token, right? In which case, what kind of numbers do we have with bitstream? Um, or bits with our bit set. Oh, which reminds me, we should probably include the bit set library. Um, yeah, include bit set. Where is that? Up here. Include bit set. And I don't know. Should we do a little investigation as to bit set? If we go to our browser, what can we say in the browser? We can say, yeah, we did a nice little thing on recursion. Don't forget to pass by reference when you want to do pass by. So how about C++ bit set? And there's a C++ reference. CPP reference. Geeks for Geeks. Bit set interesting facts. There's tutorials points, so a lot of people want to tell you about bit set, right? We should go backwards. We can start with tutorials point. Oh, we've got a nice little logo here. Absolute beginners, that's me. I'm going to feel at home here, I think. So below is a definition of the bitset header file. It's got a constructor. What is this? So there are a bunch of different, there's 4 different constructors, right? So this will just use the default value of 0. This will use a different bit value val. This will construct and initialize a bit set container. Oh, yeah, we saw this, right? You can initialize with a string object, right? Yeah, we were looking at that. So you can put the 0, 1 string in quotation, right? Well, it's a string. And this C style string, yeah. So there's you can have a C++ string or a C style string, which could be like a string literal, a pointer to a character. And then so there's the index operator, so you can get the the ith element of it's just like a string, right? And then we have the AND operation, the OR operation, the exclusive OR operation, the left shift operation, right? And so we were kind of curious about that before. So suppose you have so you're saying I've got, so this is a template, just like vector of int. This is bit set of 4. It's the same kind of angle bracket notation, right? And this is saying I've got a 4-bit number. And sure enough, there it is, described by a literal string. And if I shift by 1, then I'll get this string as my return value, right? So it shifts to the right by 1. That's what this operation does. We also have a shift to the left, I guess. And so if we have this string and you shift to the left by 1, then you get, oh sorry, left, right, who can tell the difference? I guess this is to the right, the other one was to the left. Just making it smaller when you shift to the right, making it bigger when you shift to the right. Yeah, so that was left shift, right shift. Then the negation operator, right? and we talked about that a little bit. Um, there's this bitwise left shift. How is this different from? Oh, so this one has like the little equal sign. So you got a number on the left, and this is just a single shift, right? Let's see. Do we see that here? So, oh, it looks like the same thing, doesn't it? Oh, well, this is the result equals B shifted to the right, whereas this one, well, we're kind of running short on time, aren't we? So, but yeah, I would recommend. So, how about we just copy this here as a reference and put it in our code as something we'd want to look at. Um, where can we put it? Up here somewhere? Um, yeah. Just to sort of note that yeah, we have a reference here that may be of interest to people. Um, as you're going through this. And where do we leave off here? So now we want to get a number token, right? So we switched on these. We got if we get one of those, we're going to construct an operator token and return it. And that's in any one of those cases. If we get a number token like 0, can we get like a 2? Yeah, I think, yeah, 2 is right. In fact, I'm going to just put these all in a single line here, huh? Case 2, so we could get any of the numeral digits, right? Case 3. Oh, I'm missing the colon here, huh? Case 4. Case 5. Case 6. There should be a way of generating this code automatically. Case 8. And finally case 9. Oh, that should be a 9. If you got one of those, then you want to put back the thing and get the whole integer, right? This is the way we were doing this, right? So, but put back, let's see. So that's a member of the cin. This is not our, token stream put back, but this is C. Notice that, yeah, cin does find that put back. There's no underscore in there. So put back, do we want to give it an argument? Yeah, I think put back does. Unget, you don't need an argument. That's the same sort of thing. So here's put back, and we're going to then cin dot get a character. Oh, just cin a value. Do we have a value? I don't think we have a value. So we should define our value somewhere, right? So I guess, should we just do it right here? Okay. And then we're going to return the token constructed from 8 is the queue that we've got a number token, right? And then value is the second parameter for constructing a number token. And what if we don't get one of those kind of things? Well, then we'll have the default case. Do we want to break here? I don't think so, right? Because we have a return, right? If you have the return, then there's no reason to break. You're out of there, right? But let's put in the default, which is we're going to throw an error. Bad token. We couldn't get a token, so it must be bad. It doesn't like the default there. Oh, I think I need, yeah, around here I need curly braces, right? It's a block of code. Still doesn't like it? Doesn't like these other cases, huh? Oh, I see. Because I'm still in the switch statement, right? Okay. Yeah. So yeah, that's why I didn't like those cases there. So do I need this block stuff here? Um, Obviously, it's not complaining about it. Let's keep it. Um, and I think this is now the end of the switch statement. You see that dotted line that doesn't get finished here? That means I've got an unclosed curly brace. So I close that up. Okay, now that looks good. And that's my get, which may need some fixing. Are we supposed to be getting like the semicolon character as well? Should we throw that in here? Yeah, all your operator tokens here, and maybe a quit token. Isn't that a thing? Case Q, which we don't handle what to do with that token here. We just say, you know, we can construct a quit token. All right. And oh geez, we're down to the last 7 minutes or so. Oh, actually, we get, as somebody pointed out, 12:05. So, because it's 12 more minutes. Is that going to be enough time to build anything serious here? Well, what do we need? We need a global variable for our token stream, right? So I'm going to say in global scope, right? We're not inside any function here. This is just token stream TS. And it'll use the default constructor, which is that we got an empty buffer, right? With nothing in it. It's the pants with nobody inside them. Okay, so now we need to start defining these functions. Which function shall we, which function? I'm talking about these functions here, right? Should we start with primary? Yeah, right. I mean, these are all prototypes, so we don't have to declare. They've been declared, right? So we can just start with primary, and primary is going to return an int, right? Or a bit set object. Well, I think we can interpret any int as a bit set object and do it that way, huh? So, and it doesn't take any arguments, right? And so we're going to want, the first thing primary is going to do is get a token, right? T equals token stream dot get, right? And then we're going to switch on the kind. T dot kind, right? Remember, it's a public variable, so we have access to it here, and this is a good reason to leave it public, so we can do just that. And let's see, we're going to say case that it's so if we're getting a primary, we shouldn't be getting an operator, right? We should be getting a number token or a parenthesis, right? So let's say we get a parenthesis. What do we do in that case? We get an expression. What's an expression? Well, in our case, it's an IOR expression, right? And so we want to declare int v equals, what was it? IOR expression. That's going to be a recursive call, right? Because IOR expression is going to call primary, and now primary is called IOR expression. And then we're going to get the next character, right? So token T equals ts dot get, and if T dot kind is not equal to closing parenthesis, then we're going to say, oh no, what do we say in that case? We expected a So CR, we expected a closing quote. Right? But presumably if you have a well-formed expression, then that's what we'll have, right? And then what? Well, now we're going to say, well, if we don't get a parenthesis, then we should get. Oh, do we want to return then? Yeah, primary is going to return. V, right? Yeah, V is an int, right? So then return V. I think that's going to do that, right? But what if we don't have an open? Well, then we could have a number token, right? In which case, we're just going to return the value, right? Is there anything else to do? No, I think we just say return t dot value. And we don't have to break because we're returning, right? So what if we don't get one of those two things? Well, then we're going to have our default case, right? Default. And that's going to be CR primary expected. Okay. And I think that will do it. Why is the case thing underlined? It's because I again did that funny thing with the... Alright, so this is the end of the switch statement here, right? Okay. Alright, so that's my primary. And then I will go on to define... I'm sorry, we should have... It's that damn Eulerian thing, which is still pending. What can I say? You do what you do, and you don't do more than you can do. Which I recommend you do just that. Meantime, we maybe have some dues to pay. That's due with a U. And what do I mean by that? Well, let's go to the browser. So I will post this as sort of, this is a start on where we are. Maybe I should save it, right? Because okay, so I'm going to go to the browser. I'm going to go to our website, which is here, and say somewhere in here we should have a secret place that says where are your grades, and how about A? So if you click on that A, you hope you get just that. So but how do I do this? Well, I have to do it in Dreamweaver, which means I have to pull up the grades. And for 7A, okay, and I will just copy and paste. So I need to make a new, oh crap. All right, so in Dreamweaver, I think I can do this in the remaining 5 minutes, so let's see if I can't. So in Dreamweaver, I want to open up, say, the calendar page and save it as and how do you do this? File, save as, in that same directory, a grades page. Sure. And I'm sorry the grades are in somewhat disarray, so a little behind on things, but I wanted you to know where you can check that's not on Canvas, because the Canvas grades thing just is screwed up. Or maybe I'm just an idiot and don't know how to do it. That's a speculation. Okay, so if I save this, then I think I've got it opened as grades now, right? Yeah. And so I'll get rid of the calendar, or I'll maybe change this to grades here. Oh, you can't see what I'm doing, I know. But then I'm going to click on this table, delete that, and go to my Excel page, copy this, paste it in here, and I'm afraid it's probably not even up to date with, yeah, let's see. Yeah, a few of these people I know have dropped out, so maybe I'll tidy up a little bit here. And while Sean has not dropped out, I don't see him in the room today. So Alberto, I didn't see Alberto and Max. So Kenny, I think I had something for you there, right? Okay. So, but yeah, a bunch of these people I just don't have anything for. So if you, this is part of the reason I do this, is so you can say, well, look, I turned something in there and you don't have it. Then we can reconnoiter what that situation is, right? Okay, so let me redo this. Oh, I think I have to delete the one I put in there and put in a new one. So copy that, paste it in here. And it's I'm sorry that it's the formatting is not very nice. It is what it is. Looks like I've got 6 quizzes so far. Although I think there are more and I just haven't dealt with them somehow. In any case, my dog is going ape. Let me save this, post it up there, and then go to that other page and I think that's posted now. So if I go to the calendar page and say, yeah, that little A right there, right, that's highlighted on your screen, I'm going to make a hyperlink to that and have it point to and this will at least be a starting place, if it's not, ideal at this stage. At least it's something. So now if I post the calendar page and reload that, GoDaddy, as bad as they are politically or whatever, I don't know if killing elephants is not your thing, then maybe GoDaddy is not for you. I didn't know about the elephants, but maybe if you don't know what I'm talking about, you can start page that. In any case, let's see. So I'm here, and if I now reload this page, oh look, there's it's sort of an obvious hyperlink now, isn't it? Yeah. That should be more secret somehow. I guess I could make it like a little section of the like the bottom right corner of that red zone. How about that? So if I go back to my Dreamweaver page, we are out of time, so I'll just leave it at that for now. And maybe I'll change it so it's not such an obvious hyperlink. It's only got your student number. It doesn't have your name, so I suppose these things are not that hard to cross-reference for somebody who's really assiduous and hell-bent on compromising your privacy. In any case, let me ask for questions before we break. Anything? Yeah, so if you do have some questions about whatever, just drop me an email. What I've been doing is going in the Discord for office hours. So, shall I do the Discord invite again? I can put that on. Okay, so how do you do that? Member list. Oh gosh. Question mentions help. Update ready. I've done this before, but now I can't remember. Is it over here? Uh, well, um, okay. Um, well, I'll figure it out and post it later. Meantime, not seeing any comments. We'll bring this to a close and got some unfinished business, folks. We got the memoization not quite working. I think we're close there. And the Bitwise calculator, I think that's a good way to review the whole thing. I mean, it's a fairly large program. Going through it all again with revamping based on a different object, bit set object, is I think a good exercise. So I guess I will wish you a good afternoon and a happy weekend. If I don't hear from you before Monday, I'll see you then, or in any case. And this will conclude today's session. See you Monday.